you. Oops. Testing. Is it down there? Did you close it or did you? Oh no, okay. It's not. You know how sometimes they have different. I was at right here, that one. Thank you very much. All right.
Oh, sorry.
Oh wait, the recording? Oh shoot, what happened?
Sorry. Oh, no, sorry.
That's okay. Did we start the recording?
Yeah.
Okay, I can. There we go.
Oh,
Wait, it just did it again. Hold on. Let me, that's okay. I don't know what's going on, but let's just, okay, maybe. There we go. All right. So let's come back together. Got a little bit more. We're going to talk about protein requirements, and then we'll talk about amino acid structures, and we'll see how far that gets us today, okay? Just a point that Dylan helped elucidate too. You know, when we talk about this idea of amino acid supplementation for people that are, taking these specialized 2 or 3 amino acid types of supplements, often leucine is one of them or whatever, it's not necessarily that you're going to cause them to go into a protein deficiency. That's not going to happen if you're eating a normal diet. Anna, you brought up the idea of relative quantity, right? If you're doing it when you're feeding somebody intravenously and you're just giving the bare bones of other amino acids and then you give particular other amino acids, you will cause competition and potentially cause that imbalance. So just let me be clear about that. We're not saying that it's highly detrimental for somebody to take a leucine supplement if they're eating a normal diet. It's just not worth it, right? There's not a point really to doing it because of the way that we digest and absorb protein, using whole protein, good quality, especially in the kind of diets and the kind of quantities that people tend to eat. They certainly don't need to be supplementing, with a particular amino acid that tastes bad and costs a lot of money. So is that clear to everybody? I just want to make that. Yeah. Yep. So no. So it's really in healthy people who are getting a normal healthy diet and digesting normally, okay? So that's the caveat. There are cases where providing an additional amount of glutamine, and particularly, you know how we do it, that is absorbed even better, are as peptides, small peptides. For people that have burn injury or particular intestinal problems, it can be helpful. But it is in the context of an abundant amount of other amino acids, essential amino acids, and a mix, and ideally in a peptide-based setup. Not always, right? But that's if you were trying to totally optimize absorption, digestion and absorption, that would be the way to do it. Okay, so that we're talking in the healthy state most when we think about that. And then in the unhealthy, remember I gave you the example of the pancreatic insufficiency. We're doing a peptide-based formula, and most of those are not necessarily enriched, but they might, if you had some peptide-based formulas, have a little extra glutamine in them, and those are also taken advantage and not causing problems like what I'm talking about with a healthy person. Okay, so let's talk a little bit about protein requirements, which again is, I'm sure, a review. So if you think about proteins, where are they important to us in the body? Can you throw out a few? We've already talked about enzymes, right? Are there other proteins that come to your mind as, you can say are important to us? What kind of functions do proteins have in the body besides enzymes? Your grandmother's asking. What are you learning in that dietetic program or that nutrition program? Actually, none of you probably have grandmothers that talk that way. They're probably all young and, active. And anyway, and they may know what they're talking about already. But anyway, name a protein that does something other than an enzyme. What else? Muscle tissue, okay, muscle fiber, muscle proteins. Transport, I might throw out. Can you think of a transport protein? Would you say? Hemoglobin, yeah, carries iron and oxygen. Albumin is one that we talk a lot about in MNT. So you've got carriers or transporters, you got enzymes. We just talked about amino acid and peptide transporters, right? Those are the things that bring things into cells. How about structural proteins? What keeps us together in terms of, our skin and teeth? Collagen, pretty darn important one, right? Okay, so we need protein for building those kinds of proteins. I'm sorry, we need protein in our diet to provide essential amino acids and nitrogen, but essential amino acids, so we can build the proteins that we need, right? Those structural and transport and enzymes and other things like that. Protein also provides nitrogen, and if you think about nitrogen obviously is important for the non-essential amino acids. We can construct from essential amino acids and other things. But what else is nitrogen used for? Or where else does nitrogen come in the body besides proteins? Can you think of any really important fundamental thing? So DNA, RNA, right? That's probably the most important nitrogen-containing compound that is, not protein, but definitely need nitrogen for that. So that's in a general way why we need protein. Infants and children are using the protein to grow new tissues, right? If you think about the growth that happens from the time a baby is born and growing up and all that, and then ultimately maintenance of maintenance of other tissues, and then adults we typically say they need protein to maintain what they have, right? Are there examples of conditions that you can think of where you need more than just maintenance level protein? More than the normal just to maintain. So when might you have a different situation? Yeah. Pregnancy and lactation, excellent. Yeah. Would you say? Injury, right. So injury, major surgery, anything, you can call that an injury because you've got to heal from it, right? Anything else? Those are the main ones. Oh, there might be another one. Muscular dystrophy, sure, the protein requirements to maintain and to help can be higher in a lot of different types of disease conditions like that, so that's a great example. Anyone else that would be healthy?
Maybe just like during weight loss to promote like muscle retention, so have higher amounts of protein.
Okay, so recovering from a malnourished state, sure, absolutely. And then bodybuilding, yeah, bodybuilding. They don't need to be taking free amino acids, but they do tend to take a little more. Not, most of us are eating so much protein that you probably don't need to be taking, the whopping doses that some people do. But yeah, it's an anabolic, can't speak, a condition of anabolism, similar to you've got pregnancy and lactation, you've got recovery from injury. You're first catabolic, so you're recovering from that by going into anabolism with feeding after you've had an injury or trauma or whatever. And then bodybuilding, those are probably the best examples. Now, there are some factors about protein that you need to think about. So the first one is that proteins will vary in nitrogen content depending on their amino acid makeup. Does anybody know the average percent nitrogen for protein? Those of you that are in MNT have a little bit of a disadvantage, but it's okay, you can share what you remember? Hopefully you remember. What do we say? How do you convert protein to nitrogen? I'm hearing 16%. You are right, 16%, yay. You can also divide by 6.25, but that means 16% nitrogen. So the average protein nitrogen content across, lots of sampled proteins is roughly 16%. Doesn't mean that there are not certain proteins that are higher, but that's the number that we'll think about, 16% nitrogen. And then we've got the essential amino acid content and their proportions, and we've got digestibility. And these are the two factors that determine what we call protein quality. And then we've got human variability as another issue that we just have to deal with, right? We have variability in the way we manage and react and digest protein, our needs, right? Our size, height, whatever, lots of things, human variables. So protein quality, here's just a better definition, just the ability of a protein to be digested and absorbed, and its essential amino acid content and proportions thereof. I think I talk about this later, but while you've got it on this slide, let's just write down a few of the things that dictate human variability. I mean, what are the factors that we think about? So what are the factors? What kinds of human variables influence protein requirements? And you know this because you've learned a fair amount about this, I suspect, in advanced human. Yeah. Okay, so physiologic state, whether somebody is has a illness, is one example of physiologic state. Yes, Sarah? Okay. And we don't tend to say that. If you think about the DRIs, at least I'm pretty darn sure they haven't been changed to have a male and female value. But there are factors that are relevant to that we might think about. So can you hold that thought for a second? Let's go back to physiologic state. You said acute or chronic illness, right? Could we also say growth, right? Or pregnancy and lactation, or bodybuilding, for example. I mean, all those, I guess we could lump under that sort of differing physiologic state. And Laura, you just said the other one, age, very important one. So whereas we probably wouldn't call out gender particularly, we would, although there are differences in body composition that might influence protein. Age is a very important one. So age, physiologic state. I'll just throw the third one out there because it's efficiency of digestion and absorption. We know this varies between people for various factors or reasons. Did I see another hand? Other things? Okay, yep. And physiologic state would also encompass the amount of lean tissue you have on board, when we said bodybuilders, but just in general. And that kind of accommodates potential gender differences because men tend to have more muscle mass than women. The last one's energy intake. Okay, we'll talk a little more about that, I think, at the end. I'll hold that. So let's talk about how, we said nitrogen content can vary depending on the essential amino acid composition of a protein. So I have a few structures to show you here, and I can't remember what else is on here. So we have asparagine, glutamine. So these have two. This one has two. This is tryptophan that also has two nitrogens. And we've got another one that there's more. There are more nitrogens in a particular, this one. And I've asked this question, which amino has the most. I've put the structures on here, so it's one of these three, right? And this one has the most. This has 4. Anybody know what that amino acid is? You didn't memorize these in biochem, I'm sure, right? You did? You had to memorize them? You should never have told me that. That's really funny. I had to memorize them too, and I have to say, I have to remind myself because it's not something that, comes up in casual conversation. Oh, let me draw, lysine for you. Okay, so somebody in this room remembers what that one is, or that one, possibly. This one is drawn with the chain, it's got a really long chain up here. Okay, let's go for this one. The most nitrogens of any amino acid. It's the one that ends up in the last part of the urea cycle. That's not helping you either. So this is a sign of how well it goes when we make you memorize structures, right? So I'm not going to make you memorize the structures again. But in grad school, you'll have to do it. And then you'll learn them, right, which is the way. Sometimes it helps if you're learning the actual biochemical, what's actually happening at each of the steps. It is very helpful to know structures. So at grad school level, you tend to learn the structures. Okay, no guesses, not a single one. The entire room, please. You're close. This one's lysine. You are really close, though, okay? It's kind of, I think of them sort of, I don't know. You know why I think of them together? Because they're both basic. Actually, all of these are basic, but these two are really basic. Not lysine, but it begins with an A. What'd you say? Dan kind of muffled it and said something like, name. What'd you say? Arginine. Yes, sorry, I'm not seeing where you, very good. If I had a prize, I would give you the prize. Arginine. Lysine, they're in the wrong order. There we go, okay. And histidine is this weird looking one. Proline looks a little like that too with this weird. Anyway, I'm not going to make you memorize the structures. But I do want you to know that arginine has the most nitrogen. And when I say that, it doesn't mean it's got 100 nitrogen. It's got 4. And 4 is the most you're ever going to see in an amino acid. It's the only one that's got 4, in fact. But you can see histidine's got 3 and lysine has 2, and I just put it on here. It's got 2 like the previous slides. A lot of them have 2, but it's also a basic amino acid that we're going to talk about in just a moment here. So the reason why I also want you to think about this is that if a protein has a higher proportion of arginine or histidine or lysine, it's going to have more nitrogen. So you can look at enteral formula nutrition facts labels, for Peptamen or Nutrin 2.0 or whatever. I'm not sure about Nutrin 2.0, but some of the peptide ones are 18%, and you can see it. You can read the label, and it'll say 18% nitrogen, and then it'll talk about how it's got extra glutamine, extra arginine, whatever. Impact is another one that has a lot of nitrogen-containing amino acids. Okay, so then the other thing that we can do is we can categorize protein based on their quality. And again, this is also a review, right? You remember the high biologic value proteins versus low biologic value proteins. So it's an important thing to just remind yourself what that means. All essential amino acids are present in adequate amounts, abundant and adequate. They're usually of animal origin, except gelatin is not a high biologic value protein. Gelatin does not contain tryptophan, which is one of the essentials. And then we also have some exceptions where plant proteins are high biologic value, right? Which ones do you think of? Soy is really a big one. Quinoa. Are there others that are new in the realm of grains that I don't know if kamut and some of the more ancient grains? Which it? Yeah, I don't know. Do you know that? Katarina is, I'm going to quote you here because I am not certain. I have not looked at hemp seed, hemp protein. Anyone know that for sure? Like, have you seen it? We'll just put that as a tentative and we'll double check just to make sure, just not to say that you're not trustworthy, but just because I haven't seen it. Low biologic value would be incomplete, right? They're lacking one or more amino acids, essential amino acids, not the non-essential, but the essential. The one that is, we say, is a limiting amino acid is the term for the essential amino acid that's present in the lowest amount on a percentage basis, so proportionally the lowest in relation to a reference. So the limiting amino acid is the one that is present in the lowest amount on a percentage basis when you compare it to a reference protein. And for the longest time, egg protein has been a reference. Now we use the amino acid pattern that's needed to support growth in a 1 to 3-year-old. That is so complicated to jot that in your notes, but do you know that? Is that what you learned? You didn't? Did you learn egg? Okay. It has been updated. So amino acids, to support the profile needed to support growth in a 1 to 3-year-old. And actually it doesn't make the egg is wrong. It's just that's how the World Health Organization does it, okay? So probably it's not to, both are complete proteins, like the perfect, reference type of protein to support a chicken or to support a 1 to 3-year-old. I mean, it's all kind of the same. And then I said usually plant. We talked about the exceptions, and then the concept of complementary proteins, right? And this is one of the reasons I got into nutrition, if you believe it. Sort of a lame idea, I guess, but I decided I wanted to eat vegetarian, and I started to read about combining proteins and the complementary proteins. And of course now we know it's not as complex as I probably made it when I was in college, but so the idea is you take a protein containing food that is limiting in one amino acid, like legumes where methionine is the limiting amino acid, and you mix it with grains that has a different limiting amino acid, and you complement them and you make a whole protein, right? You've heard this concept before. It's a good one. And it's how much of the world eats without having meat, right? Or a lot of places, although meat consumption is on the rise in many places. Doesn't have to be in the same meal. And I just remind us about some of the terms. Lacto-ovo vegetarians, how do they differ from a vegan diet? Someone who follows a lacto-ovo versus vegan. What's different? Milk and eggs for the lacto-ovo, right? And then there are all sorts of different configurations of people depending on what they eat, and there are different names, and we won't get into that too much, but lots of people are consuming no animal products. Vegans have to be a little more cautious, a little more careful, right, just to make sure they get adequate vitamin B12 and other things. So I think this is still roughly true that much of the world's per capita protein comes from plant protein still. And I'm sure you'll learn more about that in Advanced Humans, so I'll leave it at that. This is a label from, it is Nutrin. It's Nutrin Junior, and it just brings up these concepts. Higher biologic value. I didn't talk about net protein utilization, but that's in the Stepanek textbook. It talks about different configurations of how they evaluate these things. And it doesn't say anything about the percent nitrogen, but you can see here that the sourcing. And so whey protein, when we talk about that, it's rich in leucine, but it's also got all the other amino acids. It just has additional very high quality protein. So having half of that coming from that, it might be higher in nitrogen just because the leucine content is a little bit higher, and I think leucine I want to say it has 2 nitrogens. I'm not totally sure. Anyway, I had another label that had 18% nitrogen that I guess I removed, so I can't remember if that was that formula or not. Okay, let's talk about protein digestibility, right? Because we said that the 2 things that determine protein quality are the essential amino acid composition and the proportion, and then the protein digestibility. Most food proteins are highly digestible, right? We have evolved to deal with a very omnivorous and abundant and different variable food supply, so that's the good news. Animal proteins do tend to be better digested, that have greater digestibility than plant proteins, because some of the plants have factors that will decrease digestibility. One of which is trypsin inhibitors. Trypsin inhibitors are basically inhibiting trypsin endogenous. So they come in, you consume a protein that contains a trypsin inhibitor, and it can suppress trypsin activity. It's not going to shut off all the trypsin there, of course. That's never the way it goes. Present in some plants, and the one that is most prominent in my mind is soy protein. Okay, so soy protein has trypsin inhibitors. These are luckily inactivated by heating, right? And I don't know how many of you have had, go around eating raw soybeans, right? I don't think anyone does that really. I mean, so maybe we've evolved with the common knowledge that this isn't a great thing to do. So we eat edamame or whatever, we steam it, the Japanese method of eating them, and we cook them. And I'm not going to answer this question, so just remember what trypsin does, right? I'll have you go back and answer these questions later. Other factors that can decrease digestibility include fiber and phytates, both of which can bind proteins and decrease enzyme accessibility, the protease accessibility to the proteins just by that structural interference that can happen. And cooking can help mitigate or reduce that problem. All right, so, and then finally, the key human factors that we've already, I think we talked about these. Well, I didn't talk about body size, did we? We didn't list that one, so you can add that to the list as well. We did talk about age. So, if I say the larger the person is, or heavier, taller, typically it's true, the taller or the heavier, the greater the protein requirement. How are the DRIs for protein expressed? What is the DRI for you in this room? Most of us are in the same. I might be in a different age category, but I think it's still true for me. Okay, not as a percent. How is it? So if you say, what is the RDA for protein? What? 0.8 grams per kilogram, right? Body weight. So that's how it's determined. So protein requirements, that helps you hopefully think about body size as an important. Now, someday, maybe before I die, we'll have a way of easily assessing lean muscle, the muscle mass and lean body mass, which includes organs and other things. And we can dose protein on lean tissue as well, but we'll never actually probably do that because not everyone would get those measurements. Even if we could make absolutely great, we can do it in the research setting, but it's not all that easy. So lean tissue is really what we're targeting when we think about protein and maintenance of tissues, right? But the surrogate is body weight, right? And so we have different ways of doing it if somebody has extreme obesity. We tend to dose protein on ideal body weight, and that's a clinical thing, and so sorry again, I'm making a side note here. But for all of the healthy population, kids and adults, we have dosing based on whole body weight. We talked about physiologic state. We talked about pregnancy, lactation, growth. We talked about injury and recovery from injury and bodybuilding. Were those the four? Okay, now here's level of energy intake. So let's talk about this. Why would energy intake influence protein requirements? So let's take that question for a moment. Turn to your neighbor and talk about this, because I have a feeling you have an idea about this. So please, just a minute or two. It's doing it again. How did you stop it? How did you make it so I can advance the...
Oh,
What was it?
this and
Just like that. Okay, great. Hey, incidentally, I could have this question be part of this, but obviously you're talking, and I'm hoping you're not talking about MLK Day. What did you talk about? Why is it that energy intake can influence protein requirements? You were talking a lot, so at least, yeah, Dylan.
We were just talking about depending on how much calories you're taking in. So if it's a higher calorie amount, protein requirements wouldn't be as high because you got other energy sources that are being used in that protein.
Yep.
So you'd be sparing it easier. And then if you were
Great.
using a lower calorie diet, the protein requirements would be higher just to spare protein.
Awesome. That was extremely well articulated. Did all of you, probably you didn't hear that in the back, so let me reiterate. So essentially, if you're having an abundantly, you've got plenty of energy in your diet, your protein requirements are not as high because you're not using your protein for energy, right? You're using it, ideally, theoretically anyway, you're using it mostly for the synthetic purposes that we need to be using it for. If you have a lower energy intake so that you're not meeting your energy needs, right? So let's put it is kind of extremes to make this point. Inadequate energy intake, you're going to use your protein for some of your energy needs, right? You'll make glucose from the amino acid carbon. So your protein requirement might be higher because you're using some of it for energy. And that gets to the concept of protein sparing. So we say carbohydrate and fat are protein sparing because they give us calories that we can use for the energy that we need. And then it allows us to spare the protein, reserve it. Again, this is paper biochemistry a little bit, but it is conceptually true that we'll then use that protein for building and anabolism if we've got plenty of energy from carbohydrate and fat. Okay, so that's the concept of protein sparing and why energy intake can influence protein requirements. And then the last point we also know is the RDA or the DRI for protein differs for different groups of people. In the adult world, we say 0.8 grams per kilogram body weight, and that's minimum. And just, I mean, we talk about this in M&T. What do you think about, how many of you have assessed your own protein intake in a class in your life in this program? I hope so. No? Not everybody. Raise hands. I thought it was one of our group assignments in one of our classes that you write down what you eat. No? Maybe not? Maybe we'll do it in M&T if you haven't. How do you, can I get some levels? Have you ever figured out how many grams per kilogram? Those of you that measured it and don't feel on the spot at all, I'll give you an example of my doctoral student because that's, he's not here so I can, embarrass him. Actually, he's no longer my doctoral student. He went on to University of Wisconsin. He was taking in something like 3 grams of protein per kilogram because he's a bodybuilder. And I was always like, you don't need that much protein. So, but do you mind, Jessica? You don't feel obligated, but.
So I decided that I wanted to better calculate like what my protein needs were.
Yeah.
At my work, one of my coworkers wanted to do like a weight loss fitness challenge to get.
Yeah.
He called it sexy to the summer.
Okay.
And so I was like, well, I should probably use my, what I know about nutrition to figure out like what I actually need and then to track it.
Yeah.
So my protein needs are about like 60 grams protein per day.
So you can, well, okay, so now I'm going to ask it, I'm going to interrupt you just because, how did you calculate that? You did it based on the 0.8?
Yeah, I did based on.
Okay. What I'm going to stop you there because what I want to ask you is what were you eating before you went on that?
Yeah.
How much? Yeah.
Before I started kind of tracking, like, how much I was needing to keep it within that, I
Yeah.
was getting closer to like 85 grams of protein per day. And that
Which was,
a lot more than what I needed.
was it 1.5, 1.2?
It was, yeah, it was
Maybe
about
1.2?
that. I don't remember exactly what that, like,
Okay.
what
Yeah, the ratio, and that's okay. Thank you for sharing that. Did anyone else calculate what they're consuming on a normal? Yeah.
mine was about 1.2.
Okay. So the reality is some people are consuming even more than that, right, if they're really pushing it, like my doctoral student there, but 1.2. So you can imagine going to 0.8. And Jessica, now I would like you to share the rest of your story. How'd that feel, consuming 60 grams a day? Was that easy for you?
No, it was really hard.
Yeah.
Like, I had to do a lot of work to plan out, like, my entire day's worth of my meals.
Yep.
So that I could make sure that I was getting, protein.
Enough calories.
But that I wasn't overdoing it.
Yeah.
So it was actually really challenging, because, having to factor in, like, oh, yeah, that's right, like, this glass of milk is,
Yeah.
like,
Yep.
so that's
So thank you for sharing that, because that's something just to remind yourself, those of you that are going on and that are in MNT or have been in MNT would remember that, when we prescribe 0.8 grams per kilogram for a person who has kidney compromise, that is a painful thing to do. It's actually quite difficult. And for many of us, it's wild, for Adam, it would be impossible. And he's a dietitian, so he probably, I'm sure he hasn't followed a renal diet anytime recently. But anyway, something to keep in mind, that the DRI is not, it's the minimum requirement, and that's important to just remember that, because it's hard to, actually, most of us consume way more than that. Okay, any questions about anything that we've talked about thus far? So I'm hoping now we're probably bridging into maybe new territory, although actually biochem, you had to learn structures, so the next time will probably be more new territory, because the next bit I want to talk about is just amino acids, just so we can get on the same page and remember the qualities about amino acids that I want you to think about. So at the beginning we talked about the R group is the thing that makes an amino acid unique, right? It's the functional group, and it's the group that actually dictates the properties of the amino acid. If we talk about a basic or acidic amino acid, we've already mentioned those, right? So this is the alpha carbon, this is the alpha amino, this is the alpha carboxyl group, and that's the R group that dictates the amino acid's unique chemical and functional properties, right? So we can categorize amino acids by their R groups, whether they are acidic or basic because they've got a positive or negative charge, or they can be small or large, they can be hydrophobic, hydrophilic, they can have sulfide bonds, right? They'll be cysteine or whatever. They can be straight or other branched. We can also categorize them by essentiality, and then the last way is by the fate of their carbon skeleton, okay? And what happens to them after their amino group is removed. So let's just look at a few more amino acids so you can kind of think about them in terms of their charge. So alanine is it's not the only one, that is a good example of a neutral amino acid, meaning that at the neutral pH, or pH of the body, which is around 7-ish, there's no net charge. Anybody remember what a term is for a compound that has no net charge? It's neutral. A zwitterion. Did you hear it? I kind of heard some zzz, so I'll say that. Zwitterion. Alanine is a good example of that. Glutamate is a good example of a negatively charged amino acid at neutral pH. And then arginine, that example of amino acid that has the most nitrogen, right, is our best one example of a basic amino acid, or a positively charged amino acid. Incidentally, alanine is also one of our hydrophobic amino acids. And this is where you're going to remember this in a little bit. Next time we'll talk about the urea cycle, right? So arginine, the last step of the urea cycle actually is cleaving urea off from arginine. Okay, so you're going to learn not the I'm not going to make you draw out the structures, but it would be helpful if you remembered that from looking at it when we get to the urea cycle. Okay, here is, I call these cousins because they're glutamine and glutamate. They're very easy to get confused. And by the end of this class, you will never be confused about I'm sure of it, between glutamine and glutamate. We're going to talk more about this, but I'll just introduce that glutamine, see this nitrogen, this amino group here. Glutamine is the major carrier of ammonia between tissues. So it's the way that the body gets amino nitrogen around in a non-toxic form, okay? Because ammonia is toxic, and glutamine, a lot of different tissues will make it from their amino acid metabolism. We're going to talk about that in more specifics, but it's a very important carrier, the major one that goes between tissues. And glutamate is the major intracellular hub of amino acid metabolism. So I want you to think about these two as really important players. Neither of them are essential. Okay, they're not essential amino acids. But glutamine is the major nitrogen carrier between tissues, and glutamate is the major player in amino acid metabolism. It's the major intracellular hub. And so remember how we said this is the alpha carboxyl group down here on any amino acid and the alpha amino group. This is called a gamma carboxyl group. Okay? Glutamate has a gamma carboxyl group. We'll talk about that again in a moment. Okay, we've already talked about the example of hemoglobin. Oh boy, this is really basic, isn't it? Woof. What mineral is needed to bind oxygen? I mean, this is like, you can't graduate with a nutrition degree from, what's the answer to that? Iron, right? Okay. Critical function, so we need that. We need iron to make hemoglobin, and it allows us to bind oxygen and deliver it to the tissues. So, that's just another picture of hemoglobin. Okay. Now, we're talking about chemical properties of amino acids. So let's talk a little bit more about acidic and basic amino acids. We've already talked about how they interact within the structure of a protein, the tertiary structure, ionic interactions between positive and negative charged amino acids allow the protein to fold up in a particular way, right? And it stabilizes the protein structure. Mostly we're talking about tertiary structure here, right? Tertiary structure. And at neutral pH, normal physiology, in the blood, okay, in the tissues, the pH is around 7, right? Acidic amino acids at that pH are going to have a net negative charge. And I'm going to click just for a moment. Yeah, I added a couple of things for you, right? So this gets back to the Henderson-Hasselbalch equation, which I know you all really, well, maybe some of you. I shouldn't act as if we all don't, love. I loved biochemistry, but I wasn't. Henderson-Hasselbalch equation, the pH equals pKa. So the pKa, do you remember how important that is? So I'm going to give you kind of Carrie's world, Biochem 101, really basic stuff here. This is not rocket science, but it's important for us just to think about how denaturation and other things can happen. So the pKa of this gamma carboxyl group is 4.0. Did you learn that in biochem when you learned the structures or anything? Yes? I'm seeing mixes. So good. Okay, great. So here's a rule for you, and it's not on your slide, so you might want to just jot it down in case it's not ingrained in your brain from biochem. And actually, probably Dr. Chen has reinforced these concepts if it's necessary. So when pH is above the pKa for a particular group, the proton will come off, will dissociate. So it's like, if you are below the pKa, it's going to look like this. When the pH rises above the pKa, it's going to look like this, right? So at pH 7, that's what it's going to look like. Okay. And I've got the the other cousin set, which is aspartate and aspartic acid, similar. Gamma carboxyl pKa is 4. The same thing is going on. Whoop, my circle moved from my charge up here. So I'm just saying positively charged amino acids. Let's talk about them for a moment. At pH of 7, they're going to have a net positive charge. So arginine, I think, yeah, the pKa is 12.5, so we're never going to get below that. So here's the opposite part of that rule. When the pH is below the pKa, which 7 is always going to be below 12.5, then the proton will be there, and you will always have a positive charge on arginine. Okay? Now, what happens? We've already sort of talked about this. What happens to the charge on an acidic amino acid if the pH falls below the pKa of the gamma carboxyl group? So we have the pKa of 4. We're going to go below that. What happens to the charge on that carboxyl group? Sorry? Let's just take a moment and take a quick look at this and talk about it amongst yourselves. So remembering the rule, right? I'm not going to have, maybe I won't have us talk amongst ourselves. We're almost out of time, and I really would like to get through this little bit here before you guys have to leave. So do you want to adjust what you said? When pH is below, right? So we're below the 4, you're going to have, let's go back. Actually, it's next slide here, or we can look at this one, right? It's going to look like that, right? You fall below, it associates. Sorry, let me click. And if that happens, if within a protein, we know what that's called, right? It's disrupting all of the other types of interactions that happen in that protein structure, and it's called denaturation, right? We denature a protein when you do that. So exciting. That was so exciting, I realized. Yeah, Anna. It is making it neutral, right? It is sorry, I misspoke. It's taking that group, taking away the negative charge on it, right? And so then it becomes a zwitterion, aspartate. And I'm sorry I don't have the structure back to show you, right? But it becomes where the positive and the negative charge on the alpha carboxyl group cancel each other out because that proton is there. And that's in the case of aspartate or glutamate. Thank you. Oh, these are just so, you've had these before probably. So you think of real life examples of this. Marinating meat. Has any meat eaters out there? What do you marinate meat in, typically? That would be applying this, right? Tenderizes it and whatever. Wait, what did you say? Lemon juice? Yep. Maybe vinegar, acid, right? So you're doing that. That's a real life example that maybe your grandmother would, if you're explaining denaturation, you can talk about that with them. Nobody would do this unless you're asleep while you're getting your tea and you add milk to lemon tea. Has anyone done this? If you add cold milk into a tomato soup, what happens? It curdles. Don't do it. It's a bad idea. Kind of messes up your cream of tomato soup. But anyway, it's all the same ideas. You're denaturing that protein by hitting it with acid. Yeah, I'm passing through this fairly quickly. These are sort of, if you're really asleep, kinds of good examples. I could ask you this, and you can answer this. I'm going to leave it. pH 2 is the stomach, right? So if you go back and look at the structures and think about that, you'll realize you're taking away the negative charges. You're not doing anything to the arginine, right? The positive charged ones that have that really high pKa. So you're not changing. Those can't get more positive or whatever. You don't. But you will destabilize by removing the charges from the acidic ones, right? And then just keep in mind, it's a summary little thing here when you're going back to study, that when you denature proteins, you're making them accessible to proteolytic enzymes, right? Because you're unfolding it, and now the primary sequence is accessible. Sorry, that was a little bit of a kill the concept there. How many amino acids are there? I'm hearing 20? 20 in the classic categorization, okay? We'll say 20. And then if you think about, I think I have this on a slide, so I have to think about, we're going to name them in a second here on the next slide, but how many of them would be considered essential? What did you learn? 9? Okay. There have been some oscillations. 11. I'm going to have to think about that one with you. Essential? Oh, non-essential. 11. Yeah, sorry. I'm like, wow, I didn't hear that one. We it has gone between 8 and 9 in the past with historical reference, but we'll say 9. Okay. 3 categories: essential and non-essential. Not to be confusing, but I'm putting the indispensable, dispensable because you learn it different ways. And then we have conditionally essential. Under particular conditions where maybe your body can't meet all of the needs in sufficient quantities, to make the non-essential ones. And some examples of that. Does anybody have an idea or remember anything about an amino acid that maybe is conditionally essential, like in growth? Did you hear of anything that falls in that category? So I know arginine is one that is an example where you need more in kids. And that's not essential under normal circumstances, but it does become essential in growth. I think Laura, someone mentioned glutamine. Was it you? Yeah. Glutamine, we say, is conditionally essential under certain types of injury, metabolic stress and injury. Burn patients really could use more glutamine. Preemie infants need more cysteine and glycine. So those are a few examples for you. And histidine and kidney failure actually is another one that you may have heard of. I'm not sure how much the Stepanek book goes into that. Okay, which ones are essential? And do you have anything on your slide? Okay, then I'm not going to give you that. I flashed it, so those you have to remember it. You've memorized these, right? So let's just. Shall I help you with? Actually, maybe we should do it in order because otherwise we won't be able to do it. Let me give you the letters. The first letter. That'll help us, and I'm sure you remember it, right? What's the P? Phenylalanine, all right. Woo, shoot, I clicked too fast. Wow, that animation, it'll get you every time. Okay, valine is one. One of the T's? Tryptophan. I heard it. Would you say it louder? Who said? Threonine. Good job. Threonine. Okay, now I can click. I'm going to try to do that slowly. Oh, great. So now I have to click again. Okay, what about the M? Methionine. Very good. Another sulfur-containing one. What about the H? Histidine. I? Isoleucine. You guys you nailed it. And then the 2 L's. Leucine and lysine? Great. And what makes an essential amino acid essential? Your body can't make it, and what is it about the amino acid that you can't make? I mean, if you think about the structure, right? You got the alpha amino group, you got the alpha carboxyl group. It can't make the R group. Right? The specific functional structural properties, chemical properties of the R group can't be synthesized. I don't know if I have this on your slide, but I just want to call out the reason I have histidine in red, and this is what's kind of, you read different sources, it's still a little bit of a question, and that's because in infants, it's essential, histidine, and I didn't say that before. I said cysteine and glycine for premature infants. Histidine is one that is needed for infants. We make we conserve histidine and we produce it from various reactions, some of them at the kidney, in fact. Okay, so we can release histidine from a peptide at the kidney, but small amounts are so they may be that we need a little bit of small amounts for adults too, but it hasn't, it's not in the, we just call it essential, okay? So it's essentially essential, but there's been some question about it because we do make a little bit of it at the kidney. So I just add that thought for you. Just thinking how far we have to go here. I have 1 minute. They're out at 35. That'll end it. Okay. I'm going to stop. I'll stop at PKU and we'll answer Laura's question. Go ahead.
Well, I've just heard that some people have high levels of histamine, or maybe it's histamine and not histamine.
Oh, yes, that is a very different thing. And it is very possible for people to have high levels of histamine production, and that produces acid and other things. It's actually an amino acid derivative, but it's not histidine, so yeah, we'll keep that separate. Any other questions? Thanks for your attention this morning, and have a good day. The next